Right, so yes, we're back with a third part of the 2010 PAT. So we're still in the physics questions. We're getting onto the slightly longer ones now before we hit the really long one at the end. They're kicking off with the annoying simultaneous equations one. Bathroom contains three rubber ducks, red, green, and blue, identical shape and density, but different sizes. Length of a red duck is equal to the length of a blue duck plus the length of a green duck. The area of the base of the green duck is 4 times larger than the area of the base of the blue duck. Right, so areas are going to be, that's squaring the length. So we're saying, what was it, the base of a green duck? So green squared is going to be 4 lots of blue squared. The blue duck has a mass, it's interesting they've gone A, B, and D. The blue duck has a mass of 3 grams. What are the masses of the red and green ducks? Right, so mass, that's going to be proportional to B cubed. So we've still got a bit of work to do with a lot of these. Right, so what are we saying with all these then? So G cubed is going to be equal to, so G cubed, if we square root all of this, we get G is 2B. So we cube it and we're going to get 8B cubed. So that means that the mass of the green duck is going to have to be 8 times this 3. So we've got 24 grams for the mass of the green duck. Right, the red one is, so we just said that G is equal to 2B by squaring all of this, square rooting all of that. So we've got R is equal to 3B. So it's going to be 27 times. So the mass of the red duck is going to be equal to 81 grams. 3 times 27. Right, so that's done that bit. If when fully submersed, I wonder how it's different to submerged. Anyway, submersed, you know what I mean. The green duck displaces a total mass of water of 32 grams. What is the density of the ducks? Did they say all have the same? Yeah, they got the same density, right? So what's this? The green duck has displaced a total mass of water of 32 grams. And how much did it weigh? The green duck weighs, oh yeah, 24 grams. Right, okay. So the 24 grams, it's displaced 32 grams. So the water weighs more than the duck. So the water is of higher density than the duck. So the duck is 3/4 the density of the water. So that is going to mean that we've got 750 kilograms per meter cubed for the duck, because we know for the same volume we're getting 32 here and we're getting 24 there. So density is mass over volume. Mass is volume times density. These things have got to, if we've got exactly the same volume and we've got these different masses, then clearly we need to reduce our density down to 3/4. All right, so as the simultaneous equation questions go on these, again, that wasn't a bad one. Not as nice as the one on the last paper though, which I think was the last one. I really like that one. Right, question 23. Light from the sun has an approximate flux level of 10 to the 3 watts per meter squared at the distance of the Earth, incident on a steel frying pan of that area, total mass, that initially at that temperature. Assuming the frying pan is perfectly thermally insulated from its surroundings and absorbs all the sunlight, how long does it take for the pan to reach a temperature of 70 degrees? Okay, so we're getting, what do we need here? So 70 degrees, we need to go up 50 degrees. So we need a delta T of 50 degrees. And the mass was 2 kilograms. 2 kilograms. What's our, oh, here we go. So we got this here. So we need to go up 490 times 2 times 50. That's the number of joules we need. So we're just putting a couple of zeros on the end here. So we need 49000 joules. And we're getting, right, this is our wattage. So we're getting 10 to the 3 times 0.07 joules per second. And that is equal to 70 joules per second. So we divide one by the other, it gets seconds. So that's going to be 700 seconds. 700 seconds when you divide 49,000 by 70. Right, that's good. So we've done that one. That was our 700 seconds there. So that's definitely all we want. Yeah, thus, yeah, how long? That's that bit. Right, frying pan still at 70 degrees. Then plunged into a bowl containing 4 kilograms of water at 20 degrees C. Assuming the bowl has negligible heat capacity and no heat flow, etc., etc., what does it end up as? Okay, right, so we've put, right, there's so many different ways we could go about this. We could say you've got that amount of energy. Yeah, we've put 4,900 joules into the mix. That could be the right way to go. That's the amount that it's gone up. So now it's going to equalize it all. So if it was all starting at 20, we got 2 kilograms, which is going up at 490, I should say. And we've got, was it 4 kilograms of water, wasn't it? Yeah, 4 kilograms of water going up at 4200. So every 1 degree of rise that we get is going to have to be, so that's 980 plus, what's that, 16,800. So that's what we've got for every increase, every 1 degree C increase. So that's 80, what was that, 780, 17, yeah, 17,780 for each one. So we'll go up 2 degrees. We could just chunk this. Might be a way to do it. So you double that up would be 3,560. We're not going to get to another one, are we? Because we're going to have, if we go on top of that, we're going to have, what have we got left? So 13,440 divided by 17,780. That's what we got left over, plus our 2 degrees, because we've done 1 lot, 2 lots, and that's what we've got left. So what does that come out as? That's, and we don't have to get this too exact, do we, really? Although we can halve this a few times. Let's just do an approximation on it. So let's say that's about, I mean, 13 over 17 is going to be, or 13 over 18. This is annoying. It's come out slightly in the middle of it all. But still. Well, maybe I will halve it once. So 672. And then whatever that's going to be, well, let's round things a little bit then. So that's going to be around about 900. That's going to be around about 700. So yeah, that does make things a lot easier. 7/9 is around about 0.8. So we're looking at 2.8 degrees C rise. Oh, I only want to the nearest degree C. I should have read the question. If I read the question more closely, I wouldn't have messed around all this. You can see that's more than half. So to the nearest degree C, that is going to be going up 3. And we started at 20, so we'll end up at 23 degrees. Yeah, so that shows the value that I didn't follow my own advice of reading the question all the way to the end. To the nearest degrees centigrade, which, or Celsius, we say nowadays, yeah, would have saved my messing around over that particular fraction. But yeah, it helped that we'd worked out at the start how much energy had gone in. The fact that we've got that 49,000 joules just means we can reset everything and then say, well, let's count up again, but including the water this time. So yeah, it makes things that little bit simpler. Right, question 24 is this. Yeah, this is the last one. Astronaut arrives on planet Oceania climbs to the top of the cliff overlooking the sea. Astronaut's eye is 100 meters above the sea level. He observes the horizon in all directions at an angle. Right, okay, so we've got some planet. This guy is standing 100 meters up. So that's 100 meters. And he's looking, if he looks that way and he looks down at the horizon, then we've got 5 milliradians. Okay, so yeah, I've kind of blown this up a little bit. Right, we're going to get, let's turn this into a triangle then. So if we had turned that into a triangle, because this is a tangent, put a right angle on it, that's the radius of the planet, which is the first thing that we want to work out. And then we want to get this side. How far away is the horizon? Right. So yeah, we need to work out R and we need to work out D. This angle here is the same as that angle there. So that's going to help matters because we know that is a right angle. So that's 90 minus this, and it's also 90 minus that because this is a right angle. Right, so we've got these angles, that's also 5 milliradians there. So, well, we've got that R plus 100. I'm just doing trig relating this side and this side of this triangle. So R plus 100 times cos of, well, let's write it as 5 times 10 to the minus 3. That is equal to R. Well, this is a small angle, so we can do small angle. I'd never remembered a small angle one for cos. So let's go through it in steps because I always have to think through. It comes up so infrequently when you start doing small angles. So what we're saying is we've got some sector of a circle, but it's also a triangle, and you've got that angle there. That's our 1. So as this theta gets smaller and smaller, the angle, the triangle turns into the sector. So sine theta turns into theta because the length of the arc is r theta, or r is 1, or even if you made that r, that'd be r sine theta equals r theta, and then cancel the r's. Right, so sine theta is equal to theta in small angle. Cos theta is the square root of 1 minus sine squared. So 1 minus theta squared square root. Then we do the expansion of that and get 1 minus theta squared over 2. Right, okay. So that rings a bell now that I've seen it. So that's what we've got here. So we've got R plus 100 multiplied by 1 minus, so that's 5 times 10 to the minus 3 all squared over 2 is equal to R. So that is, well, let's multiply through by 2 on all of this because I get rid of that, put a 2 there and put a 2 there, and that makes this easier. So we've got R plus 100 multiplied by 2 minus 25 times 10 to the minus 6 is equal to R. 2R plus 200 minus 2.5 times 10 to the minus 3, and then minus 2.5 times 10 to the minus 5R is equal to 2R. So the 2R's are going to cancel. So get rid of those. And now we've just got 1R sitting around here. So we need, so R is going to be equal to 200 minus 2.5 times 10 to the minus 3 divided by 2.5 times 10 to the minus 5. Okay, so that's not going to be a lot on that second bit. We can split that into 2 fractions. So 25s into 200 is 8. So that's 8 times 10 to the 6. And that is going to dominate over this because all you're getting here is taking off, well, that becomes 1, so you're taking off 100. So who really cares about that? So 8 times 10 to the 6 meters. That's our radius. So now the d off of this. So we've got yeah, I suppose we can just stick all that in again, can't we? We can say we've got, well, we can do Pythagoras on it. So d squared plus r squared is equal to r plus 100 squared. Yeah, that seems fine, doesn't it? Do we want to do it, or do we want to do it? Actually, maybe we'd be better doing the small angle again. Yeah, I think that's going to be quicker, isn't it? We can say that r plus 100 times sine theta is equal to d, which is equal to, so it's made no difference to r by adding on 100, 8 times 10 to the 6, and then we can multiply that by theta, because sine theta is theta, 5 times 10 to the minus 3. So that's 40 times 10 to the 3, so 4 times 10 to the 4 meters. This would have worked, but you know, you're just doing a bit more effort there. If we're doing the small angle approximations, we might as well just stick with it and carry on that way. So yeah, that was quite involved, but it is all about these small angles. Like I say, I mean, this comes up so infrequently that I have to remind myself how to get some of them. The sine theta one and the tan theta one, yeah, they're both just equal to theta, so that's fine. I mean, I should remember it really. It just doesn't come up very much, so I'm not that confident when it comes to say, oh yeah, that's definitely what it is, because it doesn't just fall out of this really easily. So just making sure that I've got it right by doing that check made things okay. But yeah, otherwise this wasn't too bad. We ended up, what, 8 times 10 to the 6 meters and 4 times 10 to the 4 meters. So they were challenging questions, but they were also very manageable ones. I like that trio. That was a good batch